Welcome to Solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
For this particular problem, I want to determine W, okay, at neutral equilibrium. So we have this, right? And then we have W acting at this point, right? Uh, let's call this point this call here O, and we have there's an angle here. Let's call it theta, right? Of course, there's a spring here. Okay, let's assuming that the spring is now stretched. Okay, we have this length L over 2. Okay, to sub on the that will be at this point, so we can just determine height considering the W. Okay, and let's call it Y. Now, to solve this problem, we'll actually determine the potential function and differentiate it with respect to theta, setting it to zero to determine the equilibrium position, and take a second derivative, okay, of the potential function, and determine plug in a value, okay, and set it to zero, okay, and determine what W will give us. All right. So if we do that, we will can just come, and for W we are going to have Y, okay, to be equal to 2 2 L over 2, okay, cos theta plus L over 2 plus L over 2, okay, cos theta. So that's what we are going to have for that. Of course, which is the same thing as saying is equals to 3L over 2, okay, cos theta. All right. So having gotten that, we can just look for, therefore, our gravitational potential energy will give us, of course, we are having a positive potential energy here, okay, because the center of gravity for where W is passing through for the plug is higher than it's above at the deadroom. All right, so for the spring, we are going to have since the displacement is angular, that is, we'll be looking at 2 theta, therefore V subscript E is going to give us half, okay, half K, okay, times 2 theta, okay, we're going to square it, all right, all right, and V, the potential function, is V subscript G plus V subscript E, okay, so that if we plug in values into this, okay, this we already know, plus half 2 theta, okay, putting in values, we are going to arrive at this to be equal to 1.5 L, okay, it's going to give us 1.5 W L minus, okay, minus 1.5 W over 2. So this is what we're going to have, plus 2k theta squared. All right. So just plug in values and do that. You have, that's what we are going. This is what we are going to have. All right. But we know that cos theta is equal to 1 minus uh, theta squared over 2. So if we do that, we are going to arrive finally at, okay, so that it give, which actually gives us that, so there's no need. I've already got to that. In the process, you come across that, okay, cos theta, same thing as okay, cos theta that is there, okay, that's how we got where we came to. So if we look at the equilibrium position, we are going to have for the equilibrium position, the v, okay, the theta is going to give us equal to 0. So if we do that, we are going to arrive at minus 1.5 w L theta plus 4k theta. Okay, so that if you solve this, you arrive at theta. You do this. Of course, theta is common. Okay, you can see that theta is common. 1.5 W L is equal to 0. So that theta is equals to theta is actually equal to 0. Okay. So for the stability, all we need to do for neutral, we know that we'll take the second derivative, okay, and set it to 0 for neutral equilibrium, so that we'll have this being equal to 0. So if we do that, we are going to arrive at minus 1.5 W, when we take the second derivative, L, okay, we'll arrive at okay, L plus 4k plus 4k, so we set it to 0 condition, so that when you sub this, you will see that W will be equal to 4 equal to 4k over 1.5 L, which is also still the same thing as saying it's equal to 8 over 3 8 over 3 8 over 3 L, or same thing as saying it's K over 3 L. So this is L, the W. Okay, all right. Any one of them is correct.